Okay, so this is for those of you that don't have access to this lab at home. Even if you do want to watch it, just make sure you're doing it right. So the answer to number one is that you're going to calculate the minimum wavelength that you're going to need to shine the light on here so that these electrons would just barely make it across from the cathode over here to the anode. So we're going to shine this light, and if you haven't done the calculation, I'll give you a hint. It's 539. I've zoomed in as much as I can, but you really can't see that. But trust me, this says 539 nanometers. So basically, what's happening is that the energy of these photons coming in is just exactly equal to the energy that it needs to get the electrons out. So you have two energies here. One is the energy carried by the photon, and the other one is the energy that you need to give the electron to make it escape. So this is Tate's bale, cool Tate. His bale is, whatever sodium's is 2.304, whatever that number is. And Liza is just bringing in that exact amount of money. So I've set this for 539, and then we'll see what happens. So, if you notice what's happening, we got the light shining across here. It's hitting this. Now, this is nice because this program just shows that this thing is barely making it across. So, these electrons are gaining just enough energy from the photons to carry this across. So, they're making it. Now, the next thing we're going to do is we're going to see if this is actually the threshold. So, I want to decrease that energy of these photons just a little bit. So I'm going to take this and make this wavelength just a little bit longer. So I'm going to set this wavelength from 539 to 540. So when I set that to 540, now if you look at what's going to happen, so I've set this to 540. I've decreased the energy of these photons just a little bit. So now these electrons are still getting energy, but they haven't reached that threshold. And so this is kind of what's counterintuitive to the idea of classical mechanics. Classical mechanics would say, hey, you know, we're going to set this thing, and if we let it shine long enough, it should basically kind of like make these electrons boil, or these begin to fly off. That's not what happens. So either these electrons get enough energy and they absorb that quantity of energy to leave, or they don't. So that's one of the key things that you need to get out of that calculation. Okay, so on the next part of the lab, and sorry, got my lab over here. So then you got some questions to answer. So we set that to 540. And so on number 2, you're going to make that observation, hey, they're just barely making it across. So then we're going to set the wavelength back to, now we're going to be down to number 6, okay, excuse me, number 7. We're going to set that to 539 again, okay. So we got that. Now we're going to decrease the intensity to 50%. So now we're going to back that off to 50%. So now what's happening is that now these electrons are still coming off, okay, but the electrons are still being kicked off, but there's just not as many of them. So here's what the intensity affects. Your intensity affects the number of electrons that are being ejected, not the energy of the electrons. So with this, so we've got half as many photons hitting it, so therefore we have half as many electrons being ejected out. Now, we're going to be down to number 8, so we're going to set the intensity back to 100%, okay? And so we'll set that back to 100%. So notice as soon as I do that, I increase the number of electrons. Now, we're going to, on number 8, we're going to keep this a constant. Now we're going to change the target to the different metals. So up here on the target, which is this box up here, I can change the metal that I'm shining this on. So I'm going to change that to, from sodium, we'll try zinc. So now notice what happens when I try zinc. As soon as I shift that thing to zinc, none of the electrons are being ejected off. Okay? So we completely shut it down. So I'm still having, here's what's important. Liza is still showing up with the same money. But now we're not able to free cool Tate from jail. So that was zinc. We'll try copper. Still nothing. We'll try platinum. Still nothing. We'll try calcium. Still nothing. And we'll try the mystery metal. Still nothing. So what that means is that the binding energy for those other elements, okay, that work function, is more than what the photons are bringing in. So, in other words, Tate was the easiest one to get out of jail. Everybody else is further in jail, and Liza can't get them out because she doesn't have enough money. Okay. So now we're going to be down to number 10. We're going to put that back to sodium. Okay. Now, we're going to set the voltage to a positive 0.20 volts. So we're going to change this to positive 0.20. So down here on the bottom, okay, so this is where you can change the voltage. So I've changed this to a positive voltage of 0.20 volts. So I'm going to hit enter, okay. So now look at what happens. So I've set this as a positive 0.20 volts. Now this is really hard for you to see, but what I've done is that this is now the positive, this is with this positive 0.20, I've made this plate positive and I've made this plate negative. So these are electrons, remember, that are being ejected across here. So by making this positive and this negative, you have two things going in this direction. So they're being attracted to the positively charged plate, and they're being repulsed by the negatively charged plate. Now, then, we're going to do the same thing, but now on number 11, I'm going to set the voltage to negative 0.20 volts. So the only thing I'm going to do is I'm going to make that negative. Now, look what happens as soon as I make that a negative value. Okay? So now what's happening is that those electrons that were kicked out, so I had a positively charged plate here, I've got a negatively charged plate here, and I got to set this back, hold on, I got to change that back to, no, we're still good, we're still at 539. Somehow, so now look what happens. So at this point, we have no current flowing across, because what's happening is that by the combination of that positively charged plate on the left and the negatively charged plate on the right, we've effectively shut down this current. Okay, so now we're going to be down to number 12. We're going to set the voltage back to 0. And we're going to set the wavelength of the light to be 419. So what I've done by setting this to 419 is I've shortened up the wavelength. I've shortened the wavelength, I'm going to increase the frequency, I'm going to increase the energy of the photons that are showing up. So, now, notice what happens as soon as I do that. As soon as I do that, I'm getting some very high energy electrons that are being kicked off. So what you need to record on number 12 is I've got a current of 0.100. So what you need to record on number 12 is this current right here, 0.1 amps. Okay? So this is the current that's flowing through here. So now, notice that I've got these electrons going across, okay, with very high energy because of the fact that this isn't affecting anything, but what's happening is that I've increased the energy, I've shifted to purple light, so now these electrons are being ejected with a tremendous amount of energy. So this is like Liza showing up with like, you know, $70 and it only cost $50 to get Tate out of jail. So they're going to leave with a lot of kinetic energy because they have extra. So that's that K max value. Okay. Now, then on up here, I'm going to take this intensity. I'm going to shrink that down to 50. Okay? Now, notice what happens to the current. My current immediately drops to 0.05 amps. So I went from having a current of 0.1, where I had 100% intensity, down to a current of 0.05, because now I have basically half as many photons coming in, because I have half the intensity. Therefore, I have half the current flowing through, because I have half the number of electrons that are swiping the jet. Okay. So, now we're going to go back up to, on number 14, I'm going to return the intensity to 100%, okay? And now I'm going to increase the voltage to 0.5. Now this is going to be important. I'm going to have a positive voltage. Okay? Now, let me see. Oh, that's what's wrong. Hold on. Okay, so my intensity, I couldn't get it set back to 100%. For some reason, it was like 200% weird. Okay, now, here's what I want you to notice. Even though I've got this positive voltage of 0.5, notice that those electrons are coming across, okay, faster, but I haven't changed the current. My current is still at 0.1. So what this means is that after you cross a certain threshold, once these electrons begin to get emitted, then no matter what I do with this current, okay, beyond a certain threshold, the current's going to stay the same. So all that I'm doing is making the electrons move across here faster, but it's still the same number of electrons that are being injected over here. Okay? So on number 14, it says return the intensity, now increase the voltage to 0.5. What effect does that have on the current? It makes no difference on the current. It's still at 0.1 volts. So, just to make sure everybody's cool, your answer to number 12 is 0.1 amps. Your answer to number 13 is 0.05 amps. Your answer to number 14 is still 0.10 amps because we haven't changed anything in terms of those making it across. Now we're on the back side, or the second page, number 15. So now we're going to set the voltage to negative 0.5. Okay. So we'll throw a negative sign in there. Now, look what happens. So by making this a negative value, I've still got some electrons that are making it across. Okay? So I've still got my voltage, my current is now like 0.049, so basically like 0.05. So notice, if you notice some of these electrons, and this does a nice job of modeling. So these electrons are being kicked off, and there's various amounts of energy. So some of them are still making it across, and some of them are going like part way, and then they're going to stop, and then they're going to come back. Okay? So, and some of them go farther, and then they stop. Because what's happening is that these electrons are being kicked out from different depths within the sodium metal itself. So the ones that are making it across are the ones that are losing the least amount of energy in being kicked out. The ones that are barely making it across are the ones that were deeper in and closer to the nucleus. So it costs them more energy to get out, so they're leaving with less energy, and then they're being pulled back. So again, on this negative voltage, okay, this is important, on this negative voltage, this is my positive terminal, this is my negative terminal. So these electrons are being pulled back towards here, and then are being repelled by here. But we still have enough to make it across. Not very many, but we still have some to make it across. Now, on number 16, I want to adjust this voltage so that the electrons basically just make it across and barely stop. So I'm going to get this, I don't know, I'll try 0.6, okay? So if I go to negative 0.6, I've still got a little bit of a current going across. So let's try negative 0.65. So when I go to negative 0.65 volts, these electrons are going across, and they're just getting right over here to this positive terminal, or this negative terminal, and then they turn around and going back. So notice that my current has dropped to 0. So in terms of what you can physically manipulate in the lab, the voltage across here was the easiest thing to control. Okay? Oh, do you make it the positive terminal or the negative terminal? And then basically you turn a knob and you say, okay, how much voltage do I have across these plates? So, got the positive here, I got the negative here. The direction of the electron field would be pointing in this direction, but they're electrons, so that's why they're traveling in that direction. So, negative 0.65, that effectively shut it down. So what you want to do on number 17 is that you're going to actually calculate that value. So what I would do is that you've got the work function of the sodium, 2.304 electron volts. You got a wavelength of 419 nanometers. So basically what you want to do is realize that that 419 nanometers is carrying enough energy to kick the electrons out. So you can find your K max, set your K max. So you can find your K max, that's going to be, then set that equal to, and if I were you, I'd work in electron volts, because then your electron volts then is going to be the same as your voltage. So let me give you a hint. Your answer to number 17, okay? You need to find the energy of the photons, which would be around 3. Subtract out that work function, which is 2.304. And then that's going to get you an answer in electron volts of around 0.6. But it's going to be negative because you need to have a negative voltage. So your answer to number 17 should be a negative, somewhere between a negative 0.6 and a negative 0.7. Okay, so, and that's what that voltage is going to show you in terms of actually stopping this. Now, so on number 17, we're going to set this to, let me give you a hint, this answer is negative 0.66. So I'm going to change that to negative 0.66. Okay, and now on number 18, I'm going to set the wavelength to 409. Okay. So now, if you think this through, I've shortened the wavelength. So I've increased the frequency, and I've increased the energy of the photons that are coming in. So now when I do this, now, even though it doesn't show up as a measurable current, if you notice what happens is that I've still got, now I've started to get some of these electrons that are making it across. So here's what's important. Even though I've got this set equal to the voltage stop, okay, that equal to that K max, but because I shrunk the wavelength from 419 to 409, I've increased the energy of the photons coming in, that means now I'm going to have some electrons that are ejected with enough energy to overcome this. So when you have a negative voltage, it's like trying to make this thing roll uphill. So I'm not changing the height of the hill, okay? That's still negative 0.66. But by decreasing my wavelength, I've increased the energy. So now what happens is that now I'm giving some of these electrons enough energy to make it all the way up this incline. So I'm pushing it up the hill when it leaves this. So now, not very many of them, but you'll notice that these electrons, whoop, they just made it across. But most of them are still going to stop and turn around. Okay. Now we're going down to number 19. We're going to set the voltage back to 0. And the wavelength to 419. Intensity still 100%. Okay? So, now this is kind of the calculation portion of the stage. So, now you're going to calculate the velocity of the electrons. So, what you're going to do is that you're going to know the energy that they have coming in. So, you know this part. Here's the photon energy. It's still sodium, so you know the work function, 2.304 volts. That's going to allow you to calculate the energy that they're going to have when they leave. And from there, you can calculate that velocity. And then you can calculate the de Broglie wavelength. So on number 19, if all goes well, you should get an answer of 10 to the 5th for that velocity. And your de Broglie wavelength in nanometers would be between 1 and 3 nanometers. Okay? Okay? So on number 20, your de Broglie wavelength in nanometers is between 1 and 3. Your velocity on number 19 is 10 to the 5th. Now, on 21, I'm just going to have to take you through this. So what we're going to try and find is the unknown metal. So I'm going to change this to the unknown metal. And this is, I just got to do this. There's no cute way that I can set this. So, obviously, I'm going to try to find the identity of the unknown metal. I have to find its work function. Well, clearly, right now, nothing's happening. So I've got that wavelength set at 419, and I'm not getting any electrons kicked out. So whatever the work function is for this metal has to be more than the energy of the photons that are striking it. So what I'm going to do is that I'm going to drop my wavelength down to 285. Okay? This is just a number that I chose. Okay? You can pick any one. I just set it to 285. So, I've shrunk my wavelength down to 285 nanometers. So clearly, now I've got enough energy to kick these electrons out. So now what I'm going to do is I'm going to adjust my voltage to stop these electrons. Therefore, I will know my Kmax, or my stopping voltage. So I'm going to adjust this. I'm going to make that a certain value until I can just make this thing stop. So I'm going to set that up, and I'm going to make that a negative. We'll start to kind of slide that over. Okay. Now I went to negative 2.6. Okay, that's way too much. Okay, because I'm not even getting close to this. So maybe I'll go to negative 1.6. Okay, still too much. So I'm going to go maybe to negative 0.4. Now, if I go to negative 0.4, that's not enough because I still have a current. So whatever my stopping voltage is has to be somewhere between negative 1.6 and negative 0.4. So I'm going to try just like negative 0.6. Okay? So if I go to negative 0.6, even though I don't show a current, I still notice some of these electrons are barely making it across, so I need a little bit more negative voltage. So I'm going to try negative 0.65. Give it a little bit of a boost. Okay. So here are the numbers. This is what you need to say on 21. Okay, here's your procedure. You're trying to find the identity of this model. You're trying to find the work function. Once you find the work function, then you can figure out what this model is. So we set the wavelength to 285. So that allows us to calculate the energy of the incoming photons. We set the voltage to be negative 0.65. Okay, so that tells us how much energy that we have to stop it. Then, from there, we're going to work backwards and going to find the work function in the middle. So, in your procedure, you're going to say, hey, I'm going to shine a light at 285. That's going to create a current. Then I'm going to set my stopping voltage to negative 0.65. And then, from there, do the math to figure out the work function, and then you can figure out the identity of the middle. So that's what I'm looking for on number 21, okay? Here's your wavelength, 285. Here's your stopping voltage, negative 0.65. Okay, now on to number 20. So I'm going to set the wavelength to 300. And we'll return to metal, to sodium. Okay, and I've got the voltage set at negative 0.64. Okay. Now, here's what you're going to look at in number 22. So, what's happening, and this is, it's tough to see, but in case you can't see. So most of the electrons are making it across. But you'll notice that some of the electrons just barely make it, and then they stop and they come back. Now keep in mind, this is the positively charged plate, this is the negatively charged plate. So you're making these electrons roll uphill. So what's happening is that some of them, you're giving them enough energy to make it all the way across. Some of them, you're only giving them enough energy to roll up part of the hill, and then they're coming back down. So those electrons that are just barely making it across, those are the electrons that are closest to the nucleus, and so it's harder for, they're losing more energy in the escape process, therefore they don't have enough energy left over to make it up the hill. So there's kind of your explanation on 22. Okay, now on to number 23. So on 23, this is just a series of calculations. So on 23, keeping the voltage the same, okay, determine the force on the electron and the acceleration assuming the distance across the plate is 1 meter. Realistically, we never have it as 1 meter, but it's going to make the math work out. So on number 23, you got to go old school, maybe force equals EQ, and remember that you've got the charge, it's an electron, and you've got the voltage, which is 0.64. I'm working like absolute values on this one, so let me give you a hint. On 23, your force should be something times 10 to the negative 19th, and your acceleration should be something times 10 to the 11th. Okay? Now, on 24, you're going to calculate the velocity of the electron, assuming the work function is 2.304, without any considerations of the negative voltage. So in other words, on 24, all I want you to do is calculate the velocity of the electron as it goes flying off, knowing that you've got, and here's what you have to remember on this one, is that we've got the wavelength on, when you do 24, remember the wavelength is now 300 nanometers, okay? The wavelength is 300 nanometers. So all you're doing on 24 is you're finding K max, it's an electron, find your K max, use that to find your velocity. So on 24, your answer to number 24 should be something times 10 to the 5th, okay? So on 24, your velocity on 24 should be something times 10 to the 5th. Now, on 26, you're going to calculate, you got to go old school, maybe use that equation. You're going to calculate the distance it would take for it to stop across the gap. Your answer to number 26 should be, and this is an ish, okay? This is an ish, something around 3 meters. Then on 24, you're going to use the acceleration that you found up on 27, but now you're going to switch it to a positive velocity, so now you're going to make it speed up, because now you're going to have a positive acceleration. So what's happening on 27, we're going to switch this and we're going to make this the negatively charged plate and we're going to make this the positively charged plate. So now, instead of these electrons being pushed like up the hill, now they're going to be pushed down the hill. So your answer to number 27 should be something times 10 to the 6th. Okay? So let's review. Your answer to 24 is 10 to the 5th. Your answer to 27 is 10 to the 6th. Okay. So we're about done. And so let's set the voltage back to 0. So now we're down to 29. And energy versus light frequency. So, hold on. So, what I'm doing is we're going to do this twice. Now, you're going to kind of have to see this. It's tough. So, this is the sodium line, okay? So, this frequency, and I'm just going to have to show you this, okay, is going from 0, 0.75, 1.5, 2.25, 3. And this is like 10 to the 15th. So, this is like 0.75 times 10 to the 15th, 1.5, okay? And then this is your energy and your electron volts, which is going 0, 2, 4, 6, 8, 10, 12. So this is going from 0 to 12. And this is going from 0 to 3, which is what I've got on your graph. And so then you've got like 0.75 here. So you're at here. This line takes off. So this is the sodium line right here. So now I'm going to change that up. And then I'm going to do the calcium line. So if I do the calcium line, okay,